All right, so we're going to pick up here talking about control of blood pressure. We have short-term and long-term mechanisms of blood pressure control. In the short term, you're talking about changes to things like cardiac output and vessel diameter. Because those are muscular changes, those can occur much more rapidly. So this is under the control of neuronal control as well as hormones. So your autonomic nervous system can cause changes in vessel diameter and heart rate. And there are different hormones that also change things like vessel diameter and heart rate. And these are quicker, so they're more short-term controls of blood pressure. In the long term, this involves your kidneys, because your kidneys are basically filtering mechanisms, and they can help regulate blood volume. If you have increases in blood volume, what your kidneys can do is then decrease blood volume by creating more urine, but that takes time. Like, it takes time to make urine. So we call this the long-term mechanism of blood pressure regulation. It involves your kidneys. So they can help counteract fluctuations in blood pressure by altering your blood volume, right? So if you get an increase in blood volume, then you're going to make more urine, which means you'll pee more fluid out, which you therefore decrease your blood volume. If you get a decrease in blood volume, it's going to be more difficult to make urine. So then you don't pee as much, so then you don't get additional decreases in blood pressure. So what this slide is showing here, you guys, are basically the feedback loop we expect to see then with changes in blood pressure. So earlier we talked about how we have the common carotid arteries, which go up your neck, and then they branch into internal and external carotid arteries. This place where the internal and external carotid arteries branch off common carotid, we have something called the carotid body. And the carotid body has baroreceptors. Going back to the sensory systems, we talked about baroreceptors measure changes in pressure. So these baroreceptors, bless you, in the carotid body measure blood pressure. And they do this by sensing the degree of stretch on those carotid bodies. Okay, so what happens then is, let's say if someone gets a increase in blood pressure, right? So blood pressure increases outside of a normal range. What we'll see then is that these baroreceptors then can sense that increase in blood pressure, and they send that information to the brain, where the brain then decides what to do with that information. And if your blood pressure is too high, you can expect then there's a variety of factors that can undergo to decrease that blood pressure, right? So what we'll see then is that in the short term, your heart and blood vessels can really rapidly act to decrease blood pressure. So what could you do to the heart to decrease your blood pressure? Decrease heart rate, which would decrease cardiac output and therefore decrease blood pressure, right? How about contractility? Would you want to make your heart contract more strongly or less strongly? Yeah, you want to decrease contractility. So decreasing contractility also decreases cardiac output by diminishing stroke volume, and also therefore decreases blood pressure, right? That's what you do to your heart. That's a nervous system control, right? So if you want to decrease heart rate and contractility, what would you change then? Sympathetic, parasympathetic? What would you do? Increase parasympathetic activity, right? Because if you increase your parasympathetic activity, it's going to slow your heart rate down and potentially decrease contractility. What about blood vessels? Well, we know that vessel diameter can change the resistance, and we know that there's a relationship between resistance and pressure. So to decrease blood pressure, what would you want to do to resistance?
Dilate.
Decrease resistance, right? And you can decrease resistance by vasodilating. So vasodilators would basically be like a decrease in sympathetic activity or an increase in parasympathetic activity. By vasodilating, you decrease resistance, which also decreases blood pressure. But to a point, right? You don't want blood pressure to decrease too much, because then you can get below like a normal homeostatic range, right? So what happens if your blood pressure gets too low? We're going to see the opposite effects. Again, baroreceptors in the carotid body can sense this. They're going to send information to the brain, where the brain then decides what to do with that information. It'll tell the appropriate effector what to do, right? Now, our goal here is to increase blood pressure. And if you're using your heart and blood vessels, what could you do to your heart to increase blood pressure?
Increase contractility.
You can increase heart rate and contractility, which would both increase cardiac output, right? And if you increase cardiac output, that increases blood pressure, because those are proportional. We said that blood pressure and cardiac output are proportional. So how could you increase cardiac output? Well, you can increase heart rate through the stimulation of sympathetic nervous system, or you can increase heart rate through epinephrine and norepinephrine, those hormones. You can increase heart muscle contractility through the sympathetic nervous system as well. And if your heart muscle contracts more strongly, then you get a higher stroke volume, which increases cardiac outputs. and also blood pressure. And then what about peripheral resistance? If we want to increase blood pressure, what we want to do to peripheral resistance? Increase or decrease that resistance? Increase resistance, right? You increase resistance, you increase pressure. So the way you can increase peripheral resistance rapidly using your blood vessels is to vasoconstrict, right? And so some vasoconstrictors would be like an increase in sympathetic activity. So if you're more sympathetically active, that branch of your nervous system will cause vasoconstriction, which increases resistance and therefore increases pressure. So if you wanted someone, I'll give you guys an example. There's actually a maneuver called carotid massage, and if you massage the carotid bodies, don't do it too hard because you'll stimulate it yourself. But if you start massaging these carotid bodies, what are you doing? Are you increasing or decreasing pressure here? Increasing it. Good. So you're kind of tricking your body into thinking that blood pressure is already too high. You do this carotid massage. So you're not, even if your blood pressure is not actually high, you can trick it into thinking it's high by stimulating those baroreceptors. So then what would be the compensatory response then if you really push on those carotid bodies and start massaging? Decrease heart rate, decrease contractility, vasodilation, which would decrease blood pressure. So you can get someone's blood pressure to decrease just by massaging their neck, right? But if you do it really hard, their blood pressure can get so low that they actually faint. So you hear about those pressure points where someone gets hit in the neck. Well, not only can that disrupt blood flow to the brain, but it can also stimulate these baroreceptors, and you're basically tricking your body into thinking, hey, pressure's really high. But it's not blood pressure, it's external pressure, right? That causes your heart rate to slow down, and then your blood vessels vasodilate, your blood pressure drops out, and then the person faints. But you can do this, like if someone's blood pressure is really high, like in a kind of emergency situation, just start rubbing their neck right there. That can help to decrease their blood pressure without any drugs. So it's kind of an interesting phenomenon. And you're just taking advantage of their normal mechanisms to regulate blood pressure. That's pretty cool. There are also baroreceptors in the aorta. It's kind of harder to get to the aorta because it's behind the sternum. But the aorta also measures stretch or pressure. So there's two different mechanisms there. So it's kind of cool. This is short term, right? So what are the long-term mechanisms of blood pressure regulation? The kidneys, exactly. So that's what we're seeing here, you guys. This next slide talks about how the kidneys can regulate blood pressure in the long term. And we have direct and indirect mechanisms. We'll talk more about the kidneys and the specific details of the kidneys later. We have a whole chapter on that. But we know that the kidneys filter. And as a filter, you need blood pressure to force water across that filter to form urine, right? So if you saw a dramatic rise in blood pressure, so the blood pressure in the kidney starts to increase, you're going to see that there's more water being forced across the filtration mechanisms of your kidneys, which means you're forming more urine. So the direct mechanism here, you guys, is saying how there's a relationship between pressure and urine formation. The example they give, though, is that if you get a decrease in pressure, so if your blood pressure is low and you don't have enough pressure to filter that blood, then you're not going to make as much urine, which means you're not losing a lot of blood volume. And what was the relationship of blood volume and blood pressure? They're proportional, right? They positively correlate. So if you increase blood volume, you increase blood pressure. Well, one way you can increase blood volume is to just stop making as much urine, right? And if you don't make as much urine, then you're not changing your blood volume as dramatically, and that can lead to rises in blood pressure. But the reason why we call this a direct mechanism is that it's not due to any kind of regulation. It's just due to the anatomy of the kidneys themselves, right? We know the kidneys filter, and if your blood pressure is low, they won't filter as much. And if you're not filtering as much fluid, then you're not making as much urine and therefore not losing as much blood volume. And so that actually can lead to a rise in arterial pressure. Yeah?
Wouldn't it be dangerous because now you have more waste that's staying in your blood?
Yes, absolutely. Exactly. That's a great point. So if your blood pressure is too low for too long and the kidneys aren't filtering out those wastes, they can start to accumulate in the bloodstream. You got it. This is why when we start talking about, when we get to the kidneys later, we'll talk about why having a filtration rate that's too low is dangerous. But this is going to be more in terms of blood pressure. But you're right, like wastes play a role. And so under normal circumstances, your kidneys maintain a fairly constant filtration rate, but we'll come back to that later. Just for now, think if blood pressure increases and you have more pressure now in the kidneys, then you can filter a lot more, right? So you're making more urine. And if you make more urine, what happens to blood volume? Decreases. And what happens to blood pressure? Decreases. Good. So that's the direct mechanism. And so basically your kidneys can regulate blood pressure just by directly either making more urine or making less urine. And that's dependent on your blood pressure. So if your blood pressure is high, you'll make more urine. You make more urine to decrease blood volume. If you decrease blood volume, you decrease blood pressure. So that's actually makes sense. Or if your blood pressure is low, bless you, then you'll make less urine. If you don't make as much urine, then you're not getting such wide or dramatic changes in blood volume, and that could lead to an increase in blood pressure. So it's kind of interesting. So then when you start thinking about drugs that increase urine output, that would make sense then for hypertension or high blood pressure, because if you put someone on a diuretic, then you can have them pee out excess blood volume, and that would decrease their blood pressure. So it's kind of interesting. Now, the indirect renal mechanism is actually also a really cool mechanism, but it involves a system where the kidneys measure blood pressure. So not only is blood pressure measured by your carotid bodies and aorta, there's also blood pressure measuring mechanisms inside the kidneys. And what happens is if blood pressure is low, the kidneys, there's a type of kidney cells called extraglomerular mesangial cells, and some of these cells can release a hormone called renin if blood pressure is low. Now, what's really weird, you guys hear, is that when you get renin being released from the kidneys, renin's not just a hormone, it's also an enzyme. And as an enzyme, it can actually help, participate in chemical reactions. So what renin does, as it's released by the kidneys, is it causes the conversion of a hormone called angiotensinogen into angiotensin 1. So when blood pressure is low, the kidneys release renin. Renin converts angiotensinogen into angiotensin 1. Okay? Now, angiotensinogen is always floating around your bloodstream. Your liver makes this, and it's there as a precursor. It's inactive, but once you activate angiotensinogen, this can lead to other mechanisms that cause a rise in blood pressure. Okay? So when your blood pressure is low, what hormone is released by your kidneys? Renin, right? And then renin converts angiotensinogen, and then in fact the ogen means it's inactive. Anytime you guys see an ogen, like the suffix in anatomy or biology, ogen means like angiotensinogen is an inactive precursor to angiotensin 1. Now, even angiotensin 1 isn't in its active form. It turns out that angiotensin 1 is converted to angiotensin 2 by an enzyme called ACE, which is angiotensin converting enzyme. ACE you find in the blood vessels of your lungs. So here's the weird thing, is you got a hormone that's released by your kidneys when blood pressure is low, renin. Renin converts angiotensinogen, which is made by your liver, into angiotensin 1. Angiotensin 1 is converted to angiotensin 2 by ACE in your lungs, and then angiotensin 2 has the dramatic effects on changing blood pressure. Okay? In fact, you guys heard of an ACE inhibitor before? Yeah. Yeah. So if you put someone on an ACE inhibitor, what you're doing is you're inhibiting the conversion of angiotensin 1 into 2, so then you don't get the increases in blood pressure. So you want to put someone on an ACE inhibitor if they had hypertension, because by blocking ACE, or angiotensin converting enzyme, then you don't get angiotensin 2, which means you don't get all of these effects that stimulate a rise in blood pressure. So that's cool. So what does angiotensin 2 do? Well, angiotensin 2 is a potent vasoconstrictor. If you vasoconstrict, what does it do to resistance? It increases resistance, and that would increase blood pressure. You got it. So angiotensin 2, by causing vasoconstriction, increases blood pressure. That's cool. It turns out angiotensin 2 also makes you thirsty. So if you got angiotensin 2 in your bloodstream, it stimulates the thirst centers of your hypothalamus to become more active, and you consciously become more thirsty. If you're thirsty, you seek out liquid, water, right? Although there's some people who don't drink water, they just live on soda and stuff. But you seek out some sort of liquid, right? And if you ingest more water, what does that do to blood volume?
Increases.
Yeah, you got it. It increases blood volume, which increases blood pressure. That's cool. Angiotensin 2 also stimulates the release of two separate hormones, aldosterone and antidiuretic hormone. Okay, so what does aldosterone do for us? Yeah, it makes you retain sodium in the kidneys. And if you retain more sodium, you're also retaining water, because the sodium attracts water, and it prevents it from being lost in urine. So if you retain more sodium, you retain more water, you increase blood volume, bless you, which increases blood pressure. Okay? Angiotensin II also stimulates the release of antidiuretic hormone by the posterior pituitary gland. So think about the name, antidiuretic hormone, or ADH, right? It's going to prevent diuresis. Diuresis is water loss. So antidiuretic hormone prevents water loss by the kidneys. You retain more water, which then increases your blood volume and then therefore increases blood pressure. So that's cool. Antidiuretic hormone is also called vasopressin, right? Because it presses down on your blood vessels. Not literally, but it sounds cool. And then vasopressin would vasoconstrict. So antidiuretic hormone is also a vasoconstrictor. If you vasoconstrict, what does it do to resistance? Increase resistance, and then you increase blood pressure. Boom, check that out, you guys. So 4 different mechanisms, all effects of angiotensin II to increase your blood pressure. But they occur in different ways. So it's actually really neat. We call this the indirect renal mechanism because it involves hormones. How does it differ from the direct renal mechanism?
Direct renal mechanism is just due to the anatomy. So it's like the way the kidneys are set up, it just happens.
Good.
Like nothing is stimulating it from
Right.
external factors.
You got it. The direct renal mechanism is basically just, bless you, just filtering blood due to pressure. If you get rises in blood pressure, you get more filtration, which means you get more urine output, which decreases your blood volume and decreases your blood pressure. So due to a rise in blood pressure, you actually get an automatic decrease in blood pressure because the kidneys will make more urine as a result. So the kidneys can prevent your blood pressure from getting too high. That's pretty cool. I think you had a question, Ange.
Oh, so what tells the kidneys to stop releasing renin? So you were low in blood pressure, you got all this stuff to happen, but then what stops that mechanism?
Great question. So the question is, what prevents renin from being always released? Now it's going to be released in small quantities, but when it's released in large quantities, that's what's going to lead to rises in blood pressure. This is a negative feedback process. And so what happens then is that if renin is stimulated to be released by low blood pressure, and then the effect of it is to increase blood pressure, the fact that blood pressure is now higher inhibits more renin from being released. So remember, like negative feedback with hormones, like how thyroid hormone, when thyroid hormone was in high enough concentration, the presence of thyroid hormone inhibited additional thyroid hormone from being released. Similar to this process too. When blood pressure gets back to normal or if it's too high, then you won't get as much renin being released. Yeah, great question. Yeah.
So this controls blood pressure over the long term,
True.
even though these are hormones and all kinds of other things that could potentially, that we just said, are the short-term mechanisms as well.
That's a good question. So the thing about these hormones here, like angiotensin II, it is a hormone. We know that hormones have sort of, it takes longer to stimulate an effect, but they have longer lasting effects. That's why we kind of talk about it as being the long term, because they stimulate long-term effects. Also, these effects aren't necessarily always immediate. Vasoconstriction, yes, definitely. That's immediate. But, getting thirsty from angiotensin II would take time to seek out water and that kind of stuff. And then these hormones, like aldosterone and antidiuretic hormone, that's another kind of step in this process, which does take additional time. And, we talk about this as being kind of more of a long-term mechanism, but there are aspects of this that could be perceived as being shorter. Yeah, exactly. So, good question. So, that's the kidneys, you guys. And so, the main takeaway point about this slide is, what do the kidneys change to change your blood pressure?
Blood volume.
You got it, blood volume. In both the direct and indirect mechanisms. So in the direct renal mechanism, our kidneys can change our blood volume due to changes in blood pressure, where if you get a rise in blood pressure, then you create more urine, which decreases your blood volume and therefore decreases blood pressure. Or if you get a fall in blood pressure, then you don't make as much urine, which then will increase blood volume and increase blood pressure. That's the direct mechanism. And then all of the indirect mechanisms that involve these hormones all act to increase your blood volume or vasoconstriction and increase blood pressure. So it's pretty cool. So just to summarize this one more time, you guys, when is renin released?
Decrease in blood pressure.
Decrease in blood pressure. And then what does renin do?
Activate angiotensin.
angiotensinogen into angiotensin 1. Is angiotensin 1 like an active hormone?
No.
No, angiotensin 1 will not stimulate rises in blood pressure. Good. So how is angiotensin 1 converted to 2? ACE. Yeah, angiotensin converting enzyme, or ACE. And you find that in the lungs. Good. So angiotensin 2, once it's activated from 1 by ACE, then it has 4 main effects. So what are the 4 main effects of angiotensin 2?
Vasoconstriction.
Vasoconstriction,
Increased thirst.
thirsty, ADH, and aldosterone. Good. And then all of those act to increase blood pressure on different mechanisms, but there's 4 separate things that can act to increase blood pressure. Why have 4? Why not just have 1? You got it. Back up. Think about how important blood pressure is for your survival. And it makes sense why you'd want at least 4 separate processes to all stimulate a rise in blood pressure to make sure your blood pressure doesn't get too low. Because earlier we learned about how blood only flows from high to low pressure. But what if your mean arterial pressure starts dropping and you don't get this change in pressure? Let's say if your blood pressure is like equal throughout your body. What happens to blood flow then? You stop having blood flow. And if blood stops flowing, then tissues aren't getting their nutrients. Yeah, and that could lead to death. So we need to maintain blood pressure to keep blood flowing because it's due to a change in pressure. So this is something that's vital for your survival. However, we can take advantage of this pathway to decrease someone's blood pressure if they have hypertension, right? Like you could block ACE, right? What else could you do to maybe prevent someone from having high blood pressure? Yeah, increase water loss, right? If you can increase their urine output, then they can help pee out some of their plasma, right? And that way they decrease their blood volume to decrease blood pressure. What about sodium intake? Definitely decrease sodium intake, right? So making sure that someone doesn't have too much sodium in their diet, because if they have too much sodium, then they're also retaining a lot of water, which increases their blood volume and increases their blood pressure. Good. How about like vasoconstriction? What would you want to do? Let's say if someone's blood pressure was too high. Yeah, maybe give them a vasodilator, right, to help decrease their blood pressure. So, good job, you guys. Now, we talk about how when blood flows through tissues, we call this tissue perfusion. And perfusion just refers to the amount of flow through a particular tissue. So we need to have tissue perfusion, meet our body's metabolic needs. And if we don't get enough perfusion in our tissues to meet that tissue's needs, then we call that ischemia. Okay, so ischemia is going to be where you have a reduction of blood flow that doesn't adequately meet that tissue's needs. Like you're not bringing enough oxygen in or nutrients in due to a decrease in blood flow. But do you guys think that all tissues receive the same amount of blood flow at any moment in time? No way, right? Like right now, we just got back from lunch and we're digesting. So that we're going to see a lot more blood flow to our digestive organs than, say, our skeletal muscle, because we're just resting, right? So that we can change our perfusion based on, certain, needs of our tissues. And what you'll find then is that, you need enough tissue perfusion in your lungs for gas exchange. We need enough tissue perfusion in our digestive tract for absorption of nutrients, and enough kidney perfusion for urine formation. Now, the rate of flow is actually going to precisely match how much blood that tissue needs. So what's really cool then is our body can actually regulate blood flow to a tissue based on the needs of that tissue. In fact, you won't get too much blood flow to a tissue because a tissue will only recruit as much blood flow as it actually needs. And it's based on different chemical signaling mechanisms that we'll talk about here in a minute. Because there's different chemicals released by tissues when they're active or underactive that either cause vasodilation or vasoconstriction, right? And if you think about it, if you have a very active tissue, you want to vasodilate in that tissue, that way you can increase blood flow or perfusion. Or if you had a tissue that wasn't so active, you can vasoconstrict to reduce blood flow and therefore, prevent blood from going to a tissue that doesn't need it. So the rate of flow actually will precisely match how much that tissue needs, which is pretty cool. So what this slide shows you guys then is the difference in tissue perfusion during rest and during exercise. And this column is supposed to represent the total amount of cardiac output during rest and exercise, right? What's our cardiac output at rest? Yeah, about 5 liters. This one's saying 5.8 liters, but that's close, right? So about 5 liters or so at rest. How about during exercise? Well, this is saying 17 liters. We've learned, though, from other slides that, or from like, previous chapter on the heart, that in some people during, like trained athletes can get their cardiac output to 35 liters in a minute, which is a tremendous amount of blood flow, right? This one's just saying 17.5, so about half of that.
This is for, like, normal people.
Yeah, it'd be like normal people, exactly. So you might wonder, well, okay, so if this column represents the total amount of cardiac output, like do tissues get wide changes in perfusion if you get increases in cardiac output, right? Like let's say if your heart's only pumping out 6 liters in a minute, like is your brain going to get more blood flow during exercise if you start increasing cardiac output? No, you can see that it doesn't here, right? You see that your brain between rest and exercise still gets the same amount of blood, right? It's just, and during exercise, it's a smaller percentage of cardiac output, but it's the same number, 750 milliliters, which is basically 3/4 of a liter. So it's, it's enough blood flow to keep your brain functioning. How about your heart? We see that blood flow to the heart increases threefold. So why increase blood flow to the heart that much?
So you can have increased cardiac.
Yeah, because basically it's working hard to pump blood. It's going to need more blood flow to itself. And what are the vessels called that bring blood to the heart? Coronary vessels. Good. How about skeletal muscle? Look at this. It increases tenfold from 1.2 to 12.5. And so what we see here then is that skeletal muscles definitely need a lot more blood flow because they're way more metabolically active. So you can increase the perfusion to skeletal muscles. Your kidneys, you have actually less blood flow during exercise. Why would that be?
You don't want to produce urine.
Yeah, exactly. Let's say if you had as much blood flow to your kidneys during exercise, then you might get a decrease in blood volume that would decrease blood pressure, and that would not be very efficient for the sympathetic response or during exercise. So we'll talk about these mechanisms later, you guys, but there's mechanisms where the kidneys can actually reduce their urine output. How about abdominal organs during exercise? Yeah, exactly. You don't need to digest while you're sympathetically active. So then we see less blood flow to the digestive organs, and then then we can see reductions in blood flow to other tissues as well. Okay, like reproductive structures, that kind of stuff.
So if you're thinking really hard, could you increase blood flow to your brain?
If your brain were somehow more metabolically active, you could recruit more blood flow to that brain. Now the question though is, does thinking harder increase the metabolism of your brain? And I don't know off the top of my head. You could design an experiment to test that. I would guess probably not, but it's possible. And this isn't to say that your blood flow to the brain never changes, because while you're sleeping, you definitely get less blood flow to the brain, right? Versus while you're awake. So it's kind of interesting. That's a great question. Now, how do you get differences in blood flow then? Like, how do the skeletal muscles get more flow? And how does abdominal organs get less flow or perfusion? Something with capillaries, right? So what did we learn about earlier that we can change capillary blood flow or perfusion?
The street happens to it from many times.
Oh yeah, the capillary beds.
Capillary beds have sphincters, right?
That can close off.
Precapillary sphincters. So what if you constricted those precapillary sphincters in a capillary bed? Would that increase or decrease flow?
Decrease.
It decreased flow in that capillary bed, right? And that's what's happening with these abdominal organs is the precapillary sphincters are constricting and blood's going elsewhere instead of flowing through the capillary. What about in skeletal muscle? Would you want to relax or constrict those precapillary sphincters? Definitely, yeah. Relax those precapillary sphincters, which is like vasodilating, which increases blood flow in skeletal muscle. So it's pretty cool. Now, what this slide is showing here, you guys, is the total cross-sectional area of your blood vessels, as well as the rate of blood flow. So, based on these data, if it's the total cross-sectional area, what type of vessel is the most abundant in your body? Capillaries, right? And that would be insignificant because capillaries are where, bless you, because capillaries are where nutrients are exchanged, right? And it makes sense why they would need to be the most abundant. They're the ones that are sort of being exchanged in nutrients and wastes. And then blood flow is also the slowest through capillaries.
It takes time.
You got it. You got it. So you want blood flow to be the slowest through capillaries because it takes time to exchange those nutrients and wastes. If blood just rushed right through a capillary, then you might not have enough time to exchange those nutrients and wastes, so then it's sort of ineffective or useless. So the way you can think about this, you guys, is that if the total area of this capillary is getting wider, right, because versus other blood vessels, think about this as almost like a river widening, right? When rivers start to get really wide, they flow faster or slower? Slower, right? Look at like Clear Creek versus the Platte River up in Nebraska. Well, Clear Creek is very narrow as it goes through the canyon, and it flows very fast. And as you get, it's kind of being pushed upon. And as you get a widening of that river or creek, the water flows much more slowly. In fact, there's rivers that look like lakes because they flow so slowly. Think about this with your blood vessels. Your capillaries have the largest cross-sectional area, so they're like the widest. If they're the widest, it means they have the slowest flow. But it makes sense from the standpoint of nutrient exchange because you want that blood to flow slow enough for nutrients to be delivered into tissues and wastes to be picked up from those tissues into your bloodstream, where then those capillaries will reconverge into veins, and that's carried back towards your heart. So it's actually pretty cool. And that's basically what this slide is saying here.